right, hello, welcome everybody. I'm starting a few minutes early, but I hope that's okay. Welcome to week 3 of our Biochemistry Weekly Reviews. So this week is kind of the week where things start to come together. So we start doing some math, we start kind of learning the actual things that are happening in biochemistry, and we start putting things together in terms of what's happening in our body. Okay, so this is kind of one of the first things that we're going to talk about, as you guys can see on the screen, is post-translational modification. So post-translational modifications can affect kind of all kinds of amino acids, obviously. But the reason that they're really important is because that modification affects how the amino acid is behaving, right? So in other words, if I have a negatively charged amino acid, and then I modify it somehow, and it makes it positively charged, or it makes it neutral, or whatever, it changes its size, it can do a million things, but some of those things, most of those things, will really affect its behavior. So learning about these post-translational modifications can be really helpful for teaching us what's going on in our body. So acetylation, you guys might have heard of acetic acid, you might have heard of acetate. It's all the same thing. It's an acetyl group being added. And what an acetyl group is, it's kind of like a carboxylic group, and it looks like that, okay? So when this acetyl group is added, the way that I like to think of it is this thing is negative. Actually, I'd rather highlight that. Change that. This thing is negative. When you add it, it needs to be added in such a way that it gets rid of that negative charge. Okay, and here's what I mean by that. When you add an acetyl group, you're not adding it to, so if I have an amino acid right here, which I'm just going to call AA, you're not adding this part to it. You're adding this part that I've highlighted. Why? Because that oxygen's the reactive part of this acetyl group. So yes, you can have an enzyme catalyze a reaction, sure, but you need that negative charge, because that negative charge is what's going to actually cause the reaction. So when I add this negative to it, I either need something it can replace, or I need a positive charge to neutralize it. So let's look at cysteine, and I'm just going to draw their R groups. SH, okay, serine is basically the same thing, both an OH. Threonine is an OH split from that. And then lysine is, oh, I apologize, I should have drawn this. 1, 2, 3, 4, and then NH2 or NH3 with a positive, right? So of these, this is going to take on a negative charge, this is going to take on a negative charge, and this is going to take on a negative charge. And moreover, in addition to just taking on a negative charge, these are also not leaving groups. In other words, of these 4 choices, only lysine can take on the positive charge needed to neutralize the acetyl group being added. So lysine is the only one of these that can be acetylated. Okay, so these are a couple of the really common ones. To the best of my understanding, and this changes based on your professor, based on your semester, but from what I've been told, this semester you need to focus on phosphorylation, acetylation, and I believe methylation, but I'm not 100% sure. These are the 2 that you absolutely have to, okay? I'm not gonna highlight any of the others because I'm not certain. Actually, yeah, I should just highlight, that's easier. Sorry about that. I'm not gonna do anything with any of the rest just because I'm not certain, but these 2 are the ones that we're gonna talk about in depth, okay? So just right off the bat, phosphorylation, exactly like it sounds like. You're adding a phosphate group, right? So phosphate groups, just as a reminder, are added is a central phosphorus surrounded by 4 oxygens, okay? And the reason that a phosphate group has only 3 oxygens is because the 4th comes from the amino acid. So if we look at the amino acid side chains, this is serine, threonine, and tyrosine. In other words, all of the alcohol groups, okay? So alcohol groups are the only ones that can be phosphorylated because that alcohol group, and I'm going to change color for this, so that alcohol group becomes the 4th oxygen surrounding the phosphorus, okay? All right, acetylation, we kind of talked about it earlier. You're adding this acetyl group, it's added to lysine, and the reason that it's added to lysine specifically is because lysine has that amine group. Now you could be asking, well, why doesn't it get added to arginine? Why doesn't it get added to, asparagine or glutamine or any of those? It's kind of hard to explain, but it comes down to the mechanism. Because the mechanisms are kind of not relevant at all, I don't want to waste time talking about them. but there is an actual reason behind it, and that's something that I wanted to emphasize. Okay. The rest of these are interesting. You're mostly going to learn about them in Biochem 2 if you need to take it, or possibly in other situations that are that I'm not certain about. Okay. So that's kind of one of the things that we learn in this unit. Another thing we learn in this unit is identification. And by identification, I know that's kind of a really large statement, is you can use things like UV-vis spectroscopy. You can use things like finding masses and all these other things to figure out what kind of amino acid you have, what kind of protein you have. And so I'd like to take some time to talk about each of them. So UV-vis spectroscopy, and it gives you an absorbance peak at 280 nanometers. Okay, so this number is really, really important. Engrave it in your memory. There's fairly consistently a question related to this concept. Okay, so when you see a peak at 280 nanometers, it tells you something about the amino acids. So the amino acid that's present is either, as it says, basic, acidic, aromatic, or nonpolar. Okay. So I'm not going to take too much time on this because I know that it's a fairly straightforward concept, and I'm just going to go ahead and just say it directly. It's C. Excuse me. C. There we go. It's aromatic amino acids. So which are the aromatic amino acids? Tyrosine is one of them. I know that. Phenylalanine, so F. And finally, W, tryptophan. These three amino acids have absorbance peaks around 780. And I know this says at, it should be around. And the reason I say around is that everything can be changed by something else. So like we learned about, the C-terminus has its pKa changed. So this is around 280 because each of these is somewhere in that range. They're not going to be exactly 280. I believe one of them is, I think if I remember right, it's tryptophan, but I'm not 100% certain. But yeah, so if you see an absorbance peak around 280, it's an aromatic amino acid. Okay? All right. So if you weigh a protein and find this mass, how many amino acids were present? Okay, so this is a really interesting question, and I personally really love these questions because you can answer this by just memorizing a number. You can answer this by just memorizing 2 numbers. You can answer this by memorizing 4 numbers. And here's what I mean by that. So the average mass of an amino acid, so if I give you just some random amino acid, its average mass will be 138. Okay. Now, 138 is not the number that we use when we say the average mass of an amino acid in a protein. Why? There are 2 reasons. The first is an amino acid on its own versus a dipeptide, a polypeptide in general. And when you form a peptide bond, so I'm just going to write this off to the side, forming peptide bonds takes H2O, right? So the C-terminus of one, actually I don't want to draw it like that. Sorry, give me one moment. The C-terminus of one end and the N-terminus of the other. This will leave along with one of those as H2O. What's the molar mass of H2O? 18. Oh, that's the other thing. I apologize. This is this unit, kDa. So K is kilo, whatever you want to call it. dA is daltons. Okay, 1 dalton is the same as 1 atomic mass unit, which is the same as 1 gram per mole. Okay. So what's the molar mass of water? 18 grams per mole, or 18 daltons. Okay. And this number over here is also in daltons. Despite having learned atomic mass units and all the rest, when we discuss mass of protein, discuss mass of amino acids, we use daltons. Okay. So, like we were saying, an amino acid on its own is going to have a mass of 138 daltons. But when you put that amino acid into a protein, you lose 18 dalton because of the I guess condensation of water. So 120, not kilodalton, excuse me, dalton is the average mass of an amino acid residue. Okay, and that's a amino acid residue. And that word right there, residue, that's kind of one of the key words to look out for. When you hear amino acid residue, you know it's in a protein. When they say an amino acid on its own, it may not be in a protein, it may be in a protein, we're not really sure. But a residue is always in a protein, okay? Now, I told you there were two factors we have to consider. The first is the formation of the peptide bond. Formation of bond. The second is abundance. Okay, and here's what I mean by that. When we look at, so the average, the mass of our amino acids, it can range from something like glycine, whose H group is a hydrogen, to something like tryptophan, whose R group, whose R group looks something like this, and anywhere in between, right? And so when we think about it in terms of just this amino acid has this molar mass, this amino acid has this molar mass, add them all together, divided by the number of amino acids, we get that 138 number. But the reality is, when we consider percent abundance, so glycine is more common than tryptophan. Alanine is more common than phenylalanine. Whatever the case may be, these larger, bulkier, heavier amino acids tend to be found less abundantly, which makes sense because they take a lot more work to make. And so because of that fact, the average, I want to think of the perfect way to phrase this because it's very easy to make a mistake on it. The average mass of an amino acid residue, or I'm sorry, let me reword that. The average mass of an amino acid based on percent abundance is 128 Dalton. Okay, and once again, we have to subtract by that 18, and we get 110. Okay, so this 110 number is usually the number that we end up using, because this is the average mass of an amino acid residue based on percent abundance. Okay, I'm going to pause for a second and make sure, does anyone have any questions about that? Okay, awesome. So if there are no questions, we can just jump right into the next part, which is actually solving this problem, which I know it's taken a while. So we're told that we have a mass of 1685 kilodalton. So I'm just going to write that 1685, and I'm actually going to say 1,000 Dalton, so a million total. I'm going to divide that by 110 Dalton per residue. And the number we get out of this is E, 15,318. So don't get confused and pick B. Keep track of your units. This is kilodalton, not Dalton. Okay. Okay. So I think we're okay with that, unless anyone has any questions. Okay, then shifting gears to the next question. So, excuse me. So, native page. This is a kind of new word. And actually, we're going to do these two questions almost side by side, if that makes sense. So we're going to do the first one, and then we're going to look at the second one based on the first one, or I should say 4 and 5. So native page at some pH, some protein is going to travel, or which protein will travel further to the anode and which will travel the slowest. So what I'm actually going to do here is we're going to rank them. But first we need to understand what a native page is. So page stands for, let's see if I can remember this acronym. It's one of the ones that you never have to learn. It is, let's see. I know it. I know the last 2 letters are gel electrophoresis. It is, gosh, let's see, Polyacrylide Gel Electrophoresis. There we go. I knew it was one of those really long, strange names. So the point of it is basically what happens is we have a gel, as it's called, and you can load samples either in the middle of the gel or at one end of the gel. So I'm going to put them in the middle in this example. And you have a negative end and a positive end, and some buffer. So this is all kind of, so this is the gel in the middle. It's soaking in buffer, okay? You have this buffer at some pH, and at that pH, so maybe you have, this is sample A, this is sample B, this is C, this is D. Maybe A will go this way, and B will go slightly slower, C will go this way, and D could kind of just stay where it is, right? So what native page does is it separates by size and it separates by charge, okay? In other words, we have to figure out relative size and relative charge. So that's what we're going to do. So what I always like to do when I'm figuring out charge is first list my N-terminus and my C-terminus. And I'm just going to do that for all of these. NC, NC, N, and C. Okay? And actually, before I jump into actually figuring out charge, we need to talk about this idea of anode. So anode and cathode, you might have learned about in Gen Chem 1, you might have learned about again in Gen Chem 2, you might have learned about them all over. And one of the biggest things about anode and cathode is they always flip, right? Sometimes the anode is positive, sometimes the anode is negative, we never really know. So the way that I remember anode for the purposes of gel electrophoresis is that the anode is where the anions go. Where the anions go. So anode, anion. And in this case, that makes it so it's positive here. Okay? In other words, excuse me. In other words, the most negative thing will go as far as it can to the anode, and the most positive thing will go as far away from the anode as possible. Okay, so that just gives us a little bit of a framework. So now what we're going to do is we're going to figure out the charge. Okay, and so what we're going to do is at a pH of 7, the N-terminus will be protonated, and that makes it positive. And I'm just going to kind of speed through this because we did talk about this a bit last week, but we also have a question down below that we're going to be able to review this a little bit more. Alanine is neutral, tyrosine is protonated and neutral, histidine is deprotonated and neutral, T is threonine, threonine is protonated and neutral, S is serine, same thing, lysine is protonated and positive, and the C-terminus is deprotonated and negative. So this is going to add up to a charge of +1. Okay. All right, next one. And actually, in this case, it doesn't. The N-terminus and the C-terminus don't really play a role since they always cancel out. I'm going to list them anyways, but I'm not going to spend too much time on them. So N positive, and actually this has 4 alanine. All 4 of them are neutral, and C-terminus is negative, so this is going to add up to 0. Okay. Once again, the N-terminus is positive. Alanine is still neutral. E is glutamate or glutamic acid, which is negative at a pH of 7. T, threonine, protonated, so neutral. D is aspartate or aspartic acid, so it's going to be negative. S is serine, and it's going to be protonated, neutral. And C-terminus is once again negative, so that adds up to -2. And then finally, D, the N-terminus is positive. The 4 alanine are all neutral. The 2 glutamates, just like above, are negative. The T, and actually this is very similar to the one right above, the T is neutral, the D is negative, the S is neutral, and the C-terminus is negative, so that adds up to -3. Okay, so if we were just basing this off charge, D would be the fastest, because, so based on charge, and I'm going to underline this because this is a very important difference. It would be D, then C, then B, then A, right? Because this is going to be most negative to most positive, okay? But I told you all that native page, that gel electrophoresis in general, also takes into account size. And by size, I really should have said mass, okay? And the reason it does is if the charge is the force being applied. So I am going to bring in some physics, I apologize. So the charge is the force being applied on this gel electrophoresis. So what we're saying here is A, over in this well over here, A is being pushed upward, okay? However, the size of A is limiting it because A could be really heavy, and so that amount of force may only end up pushing it from here to there, okay? But if we apply that same force to B, which is a lot lighter, it may end up moving from that same place all the way up to here. Oh, excuse me, all the way up to here. And so we have to keep that in mind, that mass plays a role, okay? Mass plays a role, okay? So you guys might be thinking, okay, crap, we have to multiply by that 110 number, and then we have to divide all that. That's a big mess. So the easiest way to do native page is to say charge over number of amino acids. Or I should say number of amino acid residues to be more specific. And the reason that we can do that
is because if we multiply every single mass by 110, we're not really changing anything since we're multiplying A and B and C and D by that same number. It doesn't affect the proportion. If we were trying to calculate how far it would actually go, which is not anywhere really related to what we do in this class, we would have to do that. But in this case, it's a lot easier. So what I'm going to do is I'm going to say A is charge of +1 over a mass of 1, 2, 3, 4, 5, 6 amino acids. Okay, so A is +1 over 6. B is 0 over whatever, so it's going to be 0. And, oh, it's 4, excuse me, not 6. So it's going to be 0. C is 5 amino acids and a charge of -2. So -2 over 5 is going to equal -2.5. Oh, no, sorry, -0.4. Excuse me, I went backwards. -0.4. And finally, D has a charge of -3 and a mass of 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 over 9, and that's going to equal -0.33 repeated. Okay, so now, and this is a really important distinction I want to draw, when we're looking at charge over mass, when we're looking at what native page measures, C becomes the fastest because C is the most negative for the least, it has the highest charge to mass ratio that's negative. So C is going to be the one traveling closest to the anode. D is going to be next. And then because A is traveling toward the cathode, B would be next, and then finally A. And if I were to, and obviously this isn't scientific or anything, but if we were to kind of visualize this on an actual gel, 1, 2, 3, 4, this being A, B, C, and D, and the positively charged anode, which I know is confusing, and the negatively charged cathode here, C would be maybe here. Oh, and actually, I should do this in different colors since black is the default, so we'll do this. So C could travel to here, D might travel to here, B could stay where it is, and then A might be somewhere over here. Okay, does that make sense? Why it's not just D, C, B, A in terms of the why we're not just ranking by charge? And also, I guess, does anyone have any questions about that? If you do, feel free to stop me anytime, but I'm going to go to the next question. So the next question is basically the exact same, except it's got a really big difference. And the difference is, rather than a native page, we're running an SDS page. So SDS is, let me see if I can pronounce this. Sodium gosh, hang on, this is going to take me a minute. Sodium Dodecal sulfate. Okay, you don't need to know what it actually means. It's just a bunch of sulfate groups and sodiums. Okay. The important thing is SDS will denature proteins. Okay, and by that we mean it gets rid of secondary, tertiary, and quaternary structure. And you might have learned about these. I know that it's kind of right around this unit where they start being talked about. We're going to talk about this in more depth anyways, just to be safe with the next question. But I just want to get this idea kind of down. Okay, so when it does that, it also coats all proteins or polypeptides or whatever you want to call it with uniform negative charge. Okay, so it does two things. The first is it denatures the proteins, which gets rid of all secondary, tertiary, and quaternary structures. And second, it coats all proteins with a uniform negative charge. Okay, so now and then we're going to run the page. So we're not really dealing with any of like 0.1 right here. This is not really that important for us. What is important right now is that it's coating the proteins with a uniform negative charge. In other words, charge to mass ratio, this number is fixed. And all we care about now is the mass. So the thing that's going to travel closest to the anode, which again is anything negative, is going to be the lightest. Okay, the lightest of these proteins, of these polypeptides, is going to travel furthest, because since they all have the same charge and it's the lightest, it can be moved the most. Okay, so that becomes really easy because this is 6, 4, 5, and 1, 2, 3, 4, 5, 6, 7, 8, 9 amino acids. So B is now the lightest, and it's got the same charge as the rest, so it travels the furthest. Then C, then A, then D. Okay? Are there any questions about this idea? Because I know it's a little bit weird. Okay. So now we're going to kind of add one more thing to that, and this is what point 1 is about. So it denatures proteins. When it denatures a protein, we need to talk a little bit about secondary, tertiary, and quaternary structure. And I know that you guys probably have learned this and already kind of know it, but I'm just going to make sure to give a very brief overview so everyone's on the same page. So secondary structure are things like, things like hydrogen bonding, basically. So anything involving these hydrogen bondings, so something like an alpha helix or a beta sheet, that's going to be secondary structure. Tertiary structure is other intermolecular forces that basically play a role. So this would be something like dipole-dipole interactions, moving, like changing the structure. This would be the hydrophobic side is all kind of near each other, the hydrophilic side is all near each other, things like that, that can affect it but aren't changing the shape too much. And quaternary structure is when you have 2 or more polypeptides interacting. Okay? Right? So now that we have that, we can approach this next question. And this question is one that I think I've seen on, I don't want to say most exams, but a good number of them. It's a very common question, and one I would just make sure that you understand how to do. Okay? So now if you notice, I'm not giving the amino acid sequence, so we don't need to worry about charges, and we wouldn't anyways because this is SDS, so it's going to make everything a routine charge. What we care about here is that denaturing proteins, and specifically denaturing proteins getting rid of quaternary structure. Okay, so these words, monomer, tetramer, monomer, and dimer, become kind of key words for this question. And here's why. A monomer is a 1 subunit protein. Okay, so this protein is 40 kilodalton, and it's all 1 polypeptide chain. The one in letter B is a tetramer, which means it's 4 individual polypeptide chains. Okay, and likewise D is a dimer, so it's 2 polypeptide chains. So when SDS Page, or I should say when SDS denatures these these proteins, letter B is going to be split into 4 parts. Letter D is going to be split into 2 parts. These 4 parts are now not each 120 kilodalton, they're each, well, 120 over 4, so in this case 30. They're each whatever, we assume that it's about an even distribution unless otherwise told. So in this case, there's 4 30 kilodalton parts. And now suddenly, B, the heaviest one here, has become the lightest, right? Each monomer is 30 kilodalton. That's going to travel faster than A. It's not going to travel faster than C. And then actually D, this dimer, is going to be broken up into 45 kilodalton monomers. 45 kilodalton monomers. And I apologize, I'm not sure why my things are getting erased. Okay, so now we need to rank these in terms of these new monomers. There we go. So the lightest one is going to be C, so it's going to travel the furthest. Next is actually B, which was the heaviest, then A, and then D. Okay, this is something that I think gets really confusing because at first glance, B is really, really heavy, but it's really important to split it up into its parts. And I mentioned earlier, these parts generally we assume to be about equal. They don't have to be. So you could have gotten one of the monomers in, or I should say one of the tetramers in B could be 60 kilodalton, and the other 3 could all be 20. But if you're not told, assume they're all equal, okay? I hope that makes sense. And if not, again, feel free to ask. You can type it in the chat, you can raise your hand and pause me, whatever it is you'll feel comfortable doing, okay?
So I hope we're okay with that because we're going to kind of shift gears pretty much completely. And in that, we're going to talk about well, we're not really shifting gears too much. This is related to what we've been talking about. And it's the fact that an alpha helix is a secondary structure. Okay, so secondary structures are a lot more for future weeks. It's actually kind of fairly complicated. But for now, we just need to know basic ideas. And that basic idea is that an alpha helix, secondary structure, beta sheet, secondary structure, things like that. Okay? All right, number 8 is one of the more complicated parts of this unit, and it's one that I struggled with for, gosh, probably the better part of the 3 weeks while I was trying to figure it out. It just didn't make sense to me. So, and the reason it didn't make sense is because I didn't understand how to read this graph. So I'm going to do my best to take it slow, and we're going to talk about it. Okay? So salting in is this idea that something is, we'll call it really, really soluble under certain conditions. So if I have this protein, and I'm just going to draw some random shape, and I put it in water, and it doesn't want to dissolve, I can add sodium chloride. And what that does is it makes the solvent. I don't want to make it just water. It makes the solvent, though it is usually water, more charged effectively, right? There's positive charges, there's negative charges. So what this does for us is if this protein has a positive charge over here, the chlorines will go to it. If it's got a negative charge over here, the sodium will go to it, and so on and so forth. And it keeps distributing, and so these salts distribute themselves in such a way that they help break open this protein and help it dissolve. Okay? Now, okay, yes, good. Okay, I wanted to make sure I had this picture. I love this. This is a great picture. So this is as you increase the concentration of salt. At first, you're increasing the solubility of your protein because of this, right? The salts are surrounding it. They're preventing it from globbing together by being there. Oh, excuse me. I meant to erase that. That was my notes. I apologize for that. And then there's a problem. After a time, you have to salt out. Why? Because these proteins are, at the end of the day, not as good as chloride, let's say, at being negative. They're not as good as sodium at being positive. So while they do have some charge, they're not as positive or as negative as the salt. And so when you have too high a salt concentration, the salt clumps together and it keeps the proteins out, and it actually salts out your protein. So it brings it back to its solid state and it makes it insoluble. So now let's look at this with kind of fresher eyes. So the pH is something we're going to talk about at some point, but it's not as important. So the most important thing I want to draw your attentions to is concentrations. So I should say, so this is the solubility of the protein. So the protein has really high solubility, in this case at 20 millimolar. Okay, at 1 millimolar, it's less soluble. At 5, it gets a little bit better. At 10, it gets a little bit better. At 20, it gets a lot better. That is, oh gosh, okay, I'm skipping ahead. That is as we go up this kind of peak. So 20 millimolar is the top of the peak in this case, and this could be 10 or something like that. That's what this is corresponding to. As you increase the concentration of salt, you increase the solubility. That's salting in. Okay, and this pH dependence, I said we'd talk about it in a bit. I just want to add, as you get kind of further and further to either extreme, and in this case it's not that extreme, but as you do get further, what happens is the charge actually helps, right? So as you get closer and closer to this pH of 4, let's say, the protein ends up getting more charged, and so it ends up dissolving better because of that as well. Okay, now let's talk about this kind of elephant in the room. 4 molar. That's a very high salt concentration, and it results in a very, very low solubility of protein. That is salting out. Okay, so that is kind of this part of the graph. So this bullet point you see right here is 4 molar. Okay, does that make sense? Or I should say, are there any questions about that concept? Because it is fairly confusing. Okay. Well, I'm glad you guys are getting it. I didn't. It took me way too long to figure that out. Okay. So now zooming in, because yeah, okay, perfect. So there we go. Okay. So if I want to use ion exchange chromatography, and we're going to talk about, oh goodness, sorry, and we're going to talk about what that is in a little bit. On a protein with this pi, with a buffer with that pH, what kind of exchanger should we use? So ion exchange, I guess I should say this is kind of the transition. Before this, we were talking a lot about proteins and stuff. Now we're going to talk about chromatography in general. So chromatography. Okay, so chromatography as a concept, and this is what I had drawn over here that I ended up erasing, is I have this sample, and it's got some of the stuff I want, and some of this red stuff that's impurities. So how do I get rid of these impurities? And there's a bunch of different kinds of chromatography. We're going to go over a few of the more common ones, though I wouldn't be surprised if there's ones we never touch in this class because they're like more obscure. Basically, chromatography is how do I purify my solution? So generally, I apologize, that's a terrible drawing. Generally, you're going to use a column. Okay, so if you're working in a lab, if you have your organic chemistry lab, your biochemistry lab, they may not say, we're going to be doing this kind of chromatography today. They may say something like, we're going to run a column, okay? And this column is filled with some kind of like gel-like salt substance. I don't like that it's drawn like that, but it's filled with this. And then you load your solution on there, and using some difference in these physical characteristics, so maybe our this solution versus this red solution are like the one that we want. Maybe this one is positive and the red one is negative. Or maybe it's, let's see, what are a couple of the other ones? Maybe this one is a lot larger or a lot smaller. Whatever the case may be, there are quicker ways to help separate this, okay? So this could have all the black bunched together and all the red is stuck up here, just as a like an example of what it can do. So now let's talk specifically about ion exchange chromatography. So ion exchange, and like I said, it comes in two different it comes in two different varieties. Chromatography. I don't want to spell it. Okay. So there's cation exchange and anion exchange. And we're going to talk about both. Well, we're going to talk about one and then flip it for the other, really. So cation exchange is the one that we're going to talk about first. So it's exactly like it sounds like, except in this case, the quality that we're using is charge. Okay, so once again, this is our solution. This is the solute we want. The red is our impurity. Okay, so in this case, the solute that we want is negative, and our impurity is positive. Or the other way around, I'm going to do it with this as an example. Okay, so I have my column, and I'm going to draw intentionally wide so I have room to actually draw. And what I'm going to do is I'm going to put these things along the sides. Okay, and these are going to be fairly, so this is a cation exchange, so this is going to be negative. So each of these are going to be really negatively charged. Okay, and they're going to be attached to sodium ions, maybe. Okay, so now I'm going to pour my solution in. My negatively charged, like the solute that I want, these black beads, are going to pass straight through. Why? Because they're negative, this thing is negative, they're going to repel each other. Okay, so if I grab a cup, I can collect exactly what I want. Okay, now my is going to get stuck in here. Okay, so the red ones are going to get stuck to this since they're positive, and they're not going to be able to move. So then maybe 10 minutes later, once I've made sure I got all of my solute out, I may pour some kind of buffer through. Buffer, and that buffer will wash this red impurity out. Okay, and then I get a cup with just my impurity. Okay, so that's how ion exchange works. And anion is the exact same thing, except with
Here, let me draw it this way. And anion, same as cation exchange, but column is positive and attracts anions. Anions. Okay. So the reason that the cation exchange has a negatively charged column is because the negatively charged bits on the end are not what we're exchanging. We're exchanging this positive sodium with this positive red impurity. Okay? These are the things being exchanged, and that's why it's a cation exchanger. An anion exchanger would be, this is positive, and maybe it would have chloride attached. And I'm just using chloride because sodium chloride is just really easy to use. It's convenient. Everyone knows the charges, but it could be whatever you're using in this situation. So this negatively charged thing is attached. It's going to switch places with the negatively charged thing that you're looking for. Okay? So I said that we were going to use cation exchange. We can also use anion exchange to purify this exact same solution. Except in that case, what we do is, sorry, I'm trying to give myself a little more space. So what we're going to do is if we use an anion exchanger, these are all going to be positive, 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 and so on. And so when we put our solution in, now our red impurity will pass straight through. It's going to go all the way down to the bottom, and we're going to collect that first. And then the solute that we're interested in is going to get stuck here until we add a buffer. So this could be a way for us to get rid of everything and then add a buffer and collect just our solution. You can use either to get the same effect. It's just a matter of choice, availability, and maybe there's some kind of, you want to keep it within a certain pH, so you're trying to be careful, whatever the case may be. Okay. So now let's go back to our actual question. So if I have this situation, what kind of exchanger should I use? So if I have a PI of 7, PI is the isoelectric point, there we go, point. And it's basically when my protein or my peptide is neutral. When protein is neutral. Okay, and my pH is 6. So if my pH is below my PI, I'm positively charged. Positive charge. Okay, so if you're using a positive charge, you would use a cation exchanger. Okay, that said, technically either would work, but you're using this ion exchange on this protein. So you want to collect this protein. Usually you use the one with that charge because you want to do your best to separate it completely. Okay, so in this case, I use a cation exchanger with an asterisk here. Because I'd like to get my protein separate from everything. I could use an anion exchanger and just collect this at the very beginning, but that kind of defeats the purpose of the chromatography. Okay. All right, so now I'm going to hit you guys with a bunch of terms. Liquid, hydrophobic interaction, reverse phase, and affinity. So we're going to come back to this actual discussion, and we're going to talk first about liquid and reverse phase, because these are the exact same thing, but opposite, which is why reverse phase is called reverse phase. So you can use the difference in polarity to separate substances as well. So I'm going to use the same example, except I'm going to use blue and red because I think blue and red is an easier contrast. So if our blue molecules are polar and our red are nonpolar, so now instead of having something stuck to the side of my column, I'm just going to fill my column and I'm going to have what's called a stationary phase, and a mobile phase. Okay, so it's pretty much exactly what it sounds like. The column is filled with usually silica or alumina and a solvent, and so it turns into this like gel-looking thing. So that's your stationary phase. Your mobile phase is what you're going to pour into that actually ends up separating things. So let's say I decide I'm going to use a stationary phase of dichloromethane, or DCM.
this is nonpolar. Okay, so when I pour this solution in, both red and blue are just going to kind of sit at the top for a little bit. Okay, but then I add a mobile phase, and maybe my mobile phase will be methanol, and methanol is very polar. Okay, so methanol in. Oops, I didn't mean to do that. I'm going to use green actually. So methanol is coming in. So as my methanol works its way down, my polar blue solute is going to work its way down with it. It's based on that idea of like dissolves like, or just that interaction where this blue polar solute is working with the methanol because they're both polar, so they're attracted to one another. Okay. Meanwhile, my red non-polar solute is stuck here at the top because it doesn't want to travel with the methanol. Okay. This is called regular liquid chromatography, or really just liquid chromatography. I include that regular because reverse phase is the exact opposite. So in this case, stationary phase nonpolar, mobile phase polar is liquid chromatography. So again, we'll do the exact opposite. So we're going to say our stationary phase in this case, stationary phase will be polar, so it could be the methanol, and our mobile phase will be the dichloromethane. So now, oops, forgot to draw the, there we go. So now we've still got these red and these blue solute at the very top, but I'm going to add my DCM. And as my DCM comes down, now it's going to take the red non-polar solute with it. Okay. So as you guys can tell, you can kind of use either to do the same thing if you're just trying to purify. Now that said, there is a time component to this. I don't want to sit while this column is going for hours and hours and hours just to get rid of everything and then at the end finally get my blue thing, right? What I might do is collect the red if I want the nonpolar, or I'll set up this column if I want the blue solute. Okay, so you can use either for the same purpose. And actually, we can't answer this question now, right? Oh, I'm sorry, I forgot to clarify. Your eluent is your mobile phase. I should have mentioned that. So given that your eluent is your mobile phase and it's nonpolar, this is a description of reverse phase chromatography. We are going to talk about the other two. I just wanted to explain that real quick. Okay, so hydrophobic interaction and affinity are kind of similar, except not really. So hydrophobic interaction is, I would describe it as kind of being similar to, actually, yeah, they are very similar in the sense that they also have these things along the sides or just throughout them, and these things attract something. So in hydrophobic interaction, which I'll abbreviate as A, you have a bunch of these non-polar things through the sides. Okay, and we're going to use the same notation for all of these. Okay, or for this one as well, I should say. So now, when I get something non-polar, oops, I meant to. Oh goodness, what just happened? I apologize. I meant to change that to red. I don't know what happened. Where are we? Okay, there we are. I apologize for that. There we go. So now, any of my non-polar solutes will get stuck, or not really stuck, but it basically, hydrophobic interaction will have kind of a scale. So this will be the most hydrophobic, and I'll just a ton of red right here, and then it gets less red and less red and less red until the bottom. And so it'll collect the most hydrophobic things at the top, and then my polar stuff will pass straight through. Okay, so it's a really easy way to separate by polarity. Okay, and then finally, affinity chromatography is, in my opinion, one of the easier ones. So affinity chromatography, let's say I have this protein. Okay, I don't know what this protein is, but it binds really well to benzene rings. Okay, so what affinity chromatography does is it says, okay, I'm going to put a bunch of benzene rings all throughout this, and these are all benzene, I'm going to label as B, all the way down. On
pretty much everywhere, and so on and so on and so on and so on. So now when this protein comes in, along with, you know, this non-polar thing and this polar thing and a bunch of, you know, whatever else, only the protein is going to get stuck to here, and everything else is just going to pass straight through. Okay. So affinity chromatography is very specific to the solute you're trying to isolate. Okay. I hope that makes sense. I know that we're starting to run short on time, and I do want to really get through these few questions down here. I'm going to start speeding up a little bit, but again, if you have questions, feel free to ask. And if you're still confused, I will be in the drop-in tutoring right after this, so we can go over specific questions as well. Okay. So number 11 is the last form of chromatography you need to know, and it's size exclusion chromatography. And in my opinion, it's one of the coolest. Though admittedly, I think chromatography is fascinating, so I don't know if I'm the best to trust about this. So I'm going to draw this over here. So once again, you have a column. So now one of the things here is this column is going to have what's called resins. Okay, these resins all throughout. I like to think of them as beads because that's something I can see, but they're called resins. Okay, and I'm not going to draw the rest. You guys get the idea. So these resins have tiny little pores in them. Okay, and oh, I just realized this is interfering with the answers. Okay, there we go. Have tiny little pores in them. So this is exactly like it says, size exclusion. It's by size. So if I have this solute and this solute, my blue solute can fit through these little pores and it'll be forced to travel through the resins. So this blue one will be forced to go through all of this, and it's going to take a really long time to get all the way to the bottom. Okay. The red does not have this problem. The red can't fit in these resins. It's going to kind of go through. Okay. And so it's going to get to the bottom much quicker because it doesn't have kind of, it doesn't have a really winding path, if that makes sense. Okay. So let's look at these these choices. So large molecules cannot enter the pores. That's true. Okay. And it gets stuck at the top. That's the part that's false. So A is wrong. I apologize. I seem to have, okay, there's my mouse. Okay. Large molecules, we know that's not true, and they go down quicker than the small molecules outside the resin. So this is pretty much completely backwards, and it's also wrong. Large molecules enter the pores. They do go down quicker, but they go down quicker because they're outside the resin, not inside. Okay. Small molecules enter the resin and are trapped forever. Not true. Small molecules do get out, just slower. And finally, D, large molecules cannot enter the pores of the resin, which is once again true. And so they go down the column outside the resin, which is quicker. Okay. So that's most of what's been covered up till this point, and I might have worked a little bit ahead until tomorrow's lecture, just depending on your professor. I'm not 100% sure. But I do want to go through a little bit of review from the last few units because I think they're really important, and that's what we're going to spend these last 20 or so minutes on. Okay. So before we do, I'm just going to take a slight break to get a drink of water, and I'm going to give a pause for questions. Excuse me. Okay. So cysteine side chain, which just a reminder, is this thing with an SH. So it can be protonated or deprotonated, and this is specifically telling us, its specific pKa. So when you're in an exam, unless you're given a number that's specific, I would have approximated cysteine side chain to be about 8 as its pKa. Now it's giving you a specific number, we have to use it. Okay, and it's telling you what percent of it is going to be protonated at this pH and at this pH. So we're going to do the first one pretty slowly, and then we're going to do the second one a little bit quicker. So the way that I like to set this up is using the Henderson-Hasselbalch equation. So this is probably my favorite equation, plus the log of the conjugate base, that's minus, that's an A, over the acid. Okay, so I'm just going to pause for a moment and just go through this. pH is obviously pH. pKa is the pKa of the specific thing we're looking for, which is the side chain, so it's 8.18. Awesome, we have both of those. Log is logarithm. A minus
is the concentration of conjugate base present, basically. And then this is concentration of the acid present. So in this case, we're dealing with the acid is the SH part, the base is the S minus part, okay? Just to make sure I'm explaining this as well. So now I'm going to plug in the numbers. So 7.5 is equal to 8.18 plus this logarithm, okay? So getting to the ratio of A minus over HA is really easy, right? We're just going to subtract 8.18, and we're going to exponentiate, we're going to undo the logarithm, so exponentiate with base 10, and we're going to get a number that's like 0.21. I'm going to use 0.21 for convenience. It's closer to 0.208, whatever. So 0.21 is equal to the concentration of A minus over the concentration of HA. What it wants is a percent. Okay, so percent protonated. So this is where a lot of people get confused. So I want to do my best to explain this as slowly and carefully as I can. So what we're going to do is we're going to say 0.21 is the same as 0.21 over 1. Okay, and that's equal to A minus over HA. And these should still be in brackets. I apologize for dropping those brackets. Okay, that's easy, right? We're just dividing by 1. That doesn't mean anything. But now what we do is we attribute this kind of 1 to 1. So we say the concentration of A minus is going to be 0.21. The concentration of HA is going to be 1. So we're dealing with molar here. So we're going to say A minus equals 0.21 molar. Concentration of HA equals 1 molar. Okay, does that make sense? That's something I think a lot of students get confused. I get confused on from time to time. It takes me a minute to make sure I'm doing it right. So I want to make sure I ask, are we okay with this? It's a weird step. Okay, awesome. So now, the percent protonated is equal to the concentration, the concentration of HA over the total concentration, which is going to be the sum of A minus plus HA. So in this case, it's 1 over 1 plus 0.21, and really quickly, that becomes 83%. My notes have it as 82.6 or 82.7. I'm just going to say 83 for convenience. Okay. So this is the answer to this question. Now, what I always like to suggest to people is ask yourself, does this make sense before you move on? Okay. And the reason that I do that is because we have a great way to check our work. And it's not comprehensive by any means, but it's a good way to make sure you're on the right side of what you're doing. So when your pH equals pKa, 50% is protonated and 50% is deprotonated. Okay? So below, or I should say, when the pH is lower than the pKa, more gets protonated. Protonated. So let's pause and make sure that that makes sense, because right now we have a pH lower than our pKa, so we should have more than 50% protonation. In this case, the number is 83. It makes sense. We're good. But if we had gotten 27, so if I had accidentally done A minus over the total, I would have gotten 27%. It's really easy and really common to make a mistake like that, especially at the end of a longer calculation or whatever. So just make sure to check your work with something like that. Okay. And then now that we've gone through that, we're going to kind of go a little bit more quickly through 12B with the pH of 9. There's my mouse. So 9 equals 8.18 plus the log A minus over HA. Okay, once again, subtract, undo the logarithm. 9 minus 8.18. Exponentiate with a base of 10, and you get 6.6. And again, I'm rounding for convenience. 6.6 is equal to A minus over HA. So I'm going to write that as 6.6 over 1 and turn that into concentration of A minus is equal to 6.6 molar. Concentration of HA is equal to 1 molar. And then I'm looking for percent deprotonated. Percent deprotonated. Or I'm sorry, I'm looking for percent protonated still. Ignore all of that. Percent protonated is now equal still to HA over A minus plus HA. So that's going to be 1 over 6.6 plus 1, or 1 over 7.6. And the number, two significant figures, is equal to about 13%. Okay. Once again, we can ask ourselves, does it make sense? Yes, it does. And actually, we can compare this one to the one above it. So when you're, let's see, 0.7 below, you're at 83%. When you're at 0.8 above, you're at 13%. So what I mean by comparing it, oh, did I say 27 before? I meant 17. I apologize. The inverse of this is 17%, not 27. Sorry. So what I mean by that is 9 is further from the 8.18 than 7.5 is, right? 7.5 is closer. This one is much further, or not much further away, but somewhat further away, which means that this should be further from 50% than this. And it is. If we want to put the numbers to it, this is, let's see, 37% away, and this is 33% away. And so what that tells us is this is, once again, it makes sense. It's further away from the pH, and it's, what's it called? Its percent protonation is also further away, okay? All right, so we have, I believe, yeah, 5 more. So we're nearly done, I hope. What is the PI of a polypeptide chemistry? So PI, once again, is isoelectric point. So what we do is we list all the things that contribute to pH. C is, and I'm blanking, C is, how am I not remembering? I apologize. I normally know my amino acids much better than this. Amino acids, oh, C is cysteine. I don't know why I didn't know that. Okay, so cysteine does contribute to it. Oh, sorry, this is the N-terminus. N-terminus. C contributes to pH. H is histidine, it contributes. E is glutamate. M is methionine, it does not, so I'm not going to list it. I is isoleucine, so no. S is serine. T is threonine, arginine, tyrosine. And finally, the C-terminus. Okay, and now I write their pKa's below. So 9, 8, 6, 4, 13, 13, 12, 10-ish, and 4. Okay, and then I go, you can either go work your way up or work your way down. Last week, I believe I worked my way down, so this week I'm going to work my way up. So I just put them in order: 4, 6, 8, 9, 10, 12, 13, and dotted lines. I did explain how to do PI last week, but I want to make sure I don't just ignore it completely this week. So your PI, like I mentioned in one of the questions above, is when the net charge of your polypeptide, of your protein, whatever, is 0. So what we have to do is we have to ask ourselves, well, when is it 0? So we experiment. We know that the charge changes at the pKa of one of the things that has a pKa, basically. So if we look at our N-terminus, when your pKa is 9, or it's got a pKa of 9, sorry. When you're below 9, it's positive. When you're above 9, it's neutral. Cysteine and histidine and the rest have a similar scenario. So we have to say, at what point is it neutral? So starting from 4, I'm going to go down my list, and I'm also going to rank these, like put these together. So C-terminus, C, H, N, let's see, Y, R, S, and T. Okay, just because it helps me think to see them in the order of their pKa's. So below a pK, below a pH of 4, my C terminus is going to be protonated and so neutral. My cysteine is going to be protonated and neutral. Oh, oops, I meant to put E here. My apologies. E and then C is here. Yes, there we go. Well, E is also protonated and neutral. Histidine is going to be protonated, which makes it positive. C is cysteine, which is negative, or I'm sorry, neutral. N is the N terminus, which is going to be positive. Y is tyrosine, which is neutral. Arginine is positive. And then serine and threonine are both neutral. So the total, the net charge is +3. Okay, between 4 and 6, so I'm just slap a number on there and say 5. When we go through it, we get the C terminus is now negative, glutamate is now negative, and everything else is going to be the same. Histidine is going to be positive, cysteine is neutral, the N terminus is positive, tyrosine is neutral, arginine is positive, and then serine and threonine are both neutral. So when we add this up now, we get +1. Okay, and now between 6 and 8, the C terminus and glutamate are both negative. Histidine is now neutral, no longer positive. C terminus is still neutral. The N terminus is still positive. Tyrosine is neutral. Arginine is positive, and the other two are neutral. So we add this up, and we get 0. Okay. So I'm going to stop here for the sake of time because I do have only 10 more minutes to go through the last, I believe, 3 questions that I made. 4 questions, excuse me. So I'm going to stop here with this. I could keep going to these, and I would encourage you all to, just for practice. But the PI is the single point. So because of that, we have to average the two. So it's between 6 and 8 that it's neutral. We average the two, and we get a PI of 7. Okay? All right. So for a given reaction, you have those numbers. At what temperature would this reaction be spontaneous? So the way that I set this up is I say delta G naught is equal to delta H minus T delta S. And I put the knots in. I'm not going to use them just because it's a bit tedious to repeat it every time. So when delta G is less than 0, we have a spontaneous reaction, right? So what I'm going to do is I'm going to substitute this stuff into there. And I'm going to say when delta H minus T delta S is less than 0, we have a spontaneous reaction, and solve from there. So delta H, and I'm going to use joules in this case rather than kilojoules. That's something I always want to remind you of. Keep track of your units. Negative 32,000 minus 117 times T is less than 0. I'm going to add 117 T to both sides. Negative 32,000 is less than 117 times T. Divide by that number. Excuse me. You're going to get 273.5. So when the temperature is greater than negative, oh, did I dropped a sign somewhere. I think, oh, I apologize. This should be positive. My apologies. When it's, no, I'm sorry. It should be negative. Yes, it should be negative. Negative 273.5. Oh, no, it is positive. I apologize for the confusion because it's 273.5 Kelvin. And then from there, all we need to do is, I like to convert it to Celsius because it's easier. To convert to Celsius, you're going to subtract 273. Yes, let me change that. This should be positive. And so you're going to get about 0 degrees Celsius is when this becomes spontaneous. Oh, a temperature above 0 degrees, I should say. Okay. All right. So this is for the above reaction still. At 25 degrees Celsius, what is the equilibrium constant? So what I'm going to do is I'm going to say delta G. The thing that relates delta G in equilibrium is ln K. That I'm going to set that equal to this again, and I'm going to say delta H minus T delta S is equal to negative RT times the natural log of K.
I'm going to convert this to Kelvin by adding 273, and that's going to get me to 298 Kelvin. And then I'm going to plug it in. So this is a positive 32,000, because I had to change that, minus 298 times 117 is equal to negative. So in this case, since I'm using joules per mole, I need to use the value of R that corresponds to that, which is 8.314. Temperature is once again 298, and natural log of K. So this is a bit tedious to do, I know. So I'm just going to go ahead and kind of give it away for you guys. You can clean this all up. And the number you get out of it in the end, so remember that to undo the natural log, you need to exponentiate with a base of e. You get 3.18, or I'm going to say 3.2. So K is equal to 3.2. Okay. Once again, this is a place where we can check our work. Because K is equal to 3.2, that tells us that this reaction is, generally speaking, going to the right. Okay. Because we also know that at 25 degrees, this reaction is spontaneous. That tells us that spontaneous reaction goes to the right. They match up. We're good. Okay. Right. Why are many reactions coupled with ATP hydrolysis? It's not that we have too much ATP. It's also not that reactions are spontaneous and drive ATP hydrolysis. It's letter C. Okay, and I know I could have done that slower, but for the sake of time, I'm going quickly. Letter C, and the reason is the delta G naught prime of ATP being broken down into ADP and inorganic phosphate is equal to negative 30.5 or negative 31 kilojoules per mole. Okay, this is a number I strongly encourage you to remember, either 30.5 or 30, or I'm sorry, either 30.5 or 31, because I've seen this asked before. So just keep that in mind. It's a very, very spontaneous reaction. So when you have a reaction that's got a delta G of positive 20 or positive 5 or positive 10 or whatever, coupling it with ATP hydrolysis will make the net reaction very spontaneous, and it'll really help. It helps a lot of our biological processes move on. Okay. And our last question, which I apologize, I am rushing a little bit because out of respect for your time, is the equation of a Van Hoff plot. So Van Hoff plots are based on the relationship that I mentioned earlier. The fact that delta G is equal to both this and this. Okay. So by setting these two equal to each other, which I'm going to do over here, give me one moment. So it's delta H minus T delta S, and then doing a little bit of rearrangement. So I'm going to, in this case, divide by negative RT, divide by negative RT. So this gives us that the natural log of K is equal to negative delta H over R times 1 over T plus delta S over R. Okay? So the reason that we write it in this form is because this resembles a y equals mx plus b plot. Okay? So you're most likely, you've seen this on your problem set, or I've seen a few exam questions here and there about it. By graphing 1 over t versus the natural log of k, you get what should be about linear equation. That linear equation has a y-intercept equal to this y-intercept equal to delta S over R, and a slope equal to negative delta H over R. So using this, you can see if a reaction is endothermic or exothermic, and it's just a really convenient way to express reaction. Okay. So unfortunately, it doesn't seem like we have time for questions, but if you do need help, I start in the drop-in tutoring lab right after this. I do take a short break just if I need to use the restroom or grab something to eat, but I will be in there from 5:30 until we close. Yeah, thank you all so much for coming. I'm going to go ahead and stop the recording.